All right, let's talk about concavity in the second derivative test. So what is concavity? The definition says, let f be differentiable on an open interval I. The graph of f is concave upward on I when f prime is increasing on the interval and concave downward on I when f prime is decreasing on the interval. So what does that mean? Remember, f prime, the derivative, is the slope, right? So if the slope is increasing, think about what happens. The slope is increasing. Okay, that would be a situation like this. Here I have a graph. Okay, this is concave upward. So the slope is a very small negative number here, and it's getting closer and closer to a slope of 0, which it reaches right here. And now it's getting bigger and bigger and bigger. This thing has a slope that is increasing all the time. So that's concave upward. Now, if we look at the other situation, where we have concave down, okay, this is a big slope here, and it's getting smaller and smaller until it reaches 0. And now it's going negative, so it's getting smaller and smaller and smaller. So that's concave down. So if the slope is decreasing, then it's concave down. If the slope is increasing, it's concave up. Here's another way you can look at it. Okay, this is concave up. All the tangent lines are below the curve. Okay, if they were above the curve, they would be secant lines because they would cross the graph twice. But these are tangent lines. They touch the graph only once. They're always below the curve. Okay, conversely here, it's concave down. All the tangent lines are above the curve. So the test for concavity, let f be a function whose second derivative exists on an open interval I. If f double prime of x is bigger than 0 for all x and I, then the graph of f is concave upward. And if f double prime of x is less than 0 for all x and I, then the graph of f is concave downward. So let's determine the open intervals on which the graph of f of x is 6 over x squared plus 3 is concave up or down. First thing I'm going to do is I'm going to take this thing and rewrite it. F of x is going to be 6 times x squared plus 3 to the negative 1. That'll be a little bit easier to differentiate. Okay, and so f prime of x is going to be negative 6 times x squared plus 3 to the negative 2. Use the chain rule, times 2x. So we'll rewrite this. In the numerator, I'm going to have negative 12x. In the denominator, I'm going to have x squared plus 3 squared. All right, now I got to take the second derivative. So f double prime of x, I'm going to have to use the quotient rule. Okay, so that's going to be x squared plus 3 squared times the derivative of the numerator is negative 12 minus negative 12x times the derivative of the bottom of this thing is going to be x squared plus 3 to the first power times 2x. And that's all going to be over x squared plus 3 squared, which is going to make this the fourth power. All right, let me double check, make sure I got all my negatives correct here. Yeah. Okay, so we got to play around with this and clean this up a bit because this is a bit of a mess. Let's see. I'm going to put my negative 12 out here in front. And let's see, we can cancel those negatives. So this is going to be a plus. We've got a 24 x squared plus 3. Looks like we've got an x squared plus 3 in every term here. So I can cancel one of these, that one, and one of these. So let's simplify this a little bit. Okay, so essentially one of these canceled that one and canceled one of those. Can I simplify this more? Let's see, if I distribute this, this is negative 12x squared minus 36 plus 24x squared all over x squared plus 3 to the third power. I feel like I have a negative sign here wrong somewhere. Well, let's see here. This would be, if I combine my like terms, I get 12x squared minus 36 over x squared plus 3 cubed. And somewhere I've got something wrong with the negative sign. Stand by while I figure that out real quick. Okay, I found my mistake here. So in this line right here, so remember it's x squared plus 3 squared times the derivative of the numerator is negative 12 minus the numerator, negative 12x, times the derivative of the numerator. So that should have been 2 times this. I forgot that there's a 2 right in there, times x squared plus 3 to the first power times 2x. Okay, so that changes some stuff here. That makes this 2 times 2 times 12 is going to be 48 instead of 24. And then, so then we still cancel out that, and this is still going to be 48 right here. And I distribute that in so that this is a 48 right here. And 48x squared minus 12x squared makes this 36x squared. All right, now we're cooking with gas. And so then we've got, this is 36 times x squared minus 1 over x squared plus 3 cubed. All right, so there is my equation. There's my second derivative. Now, when is that derivative equal to 0? Well, if I take the numerator and set it equal to 0, that's going to be plus or minus 1. So this thing is going to have critical points here, essentially at plus or minus 1. So I can region test this thing, and I would region test it at, so it's going to break the graph up. I would region test it, find f double prime of negative 2. I'd find f double prime of 0, and I'd find f double prime of positive 2. And let's see, if I plug in negative 2, again, all I need to know really is it going to be positive or negative? So if let's do 0, that's going to be easy. That's going to be negative 36 on the top, and on the bottom, it's going to be 3 cubed, which is going to be 27. This is negative, so this is going to be concave down. Okay, does that go with my graph? Yep, it sure does. It's concave down at 0. Okay, and then if I plug in 2 squared is going to be 4 minus 3, or 1 is 3 times, that's going to be 108 on the top over there. And it's going to be 4 times 7 cubed is a positive number. 49, I don't know what 7 cubed is. 343 or something. 343. So it doesn't really matter what it is. It's positive, so it's concave up. And the same thing is going to be true here because you're going to square the -2 in both cases, so it's going to be the same answer. So it's going to be concave up. Okay, so kind of got this picture that I threw on here a couple of years ago. X cubed plus 2x squared minus 5x plus 1. So that's this kind of purple curve right here. Okay, there's my f of x. Now the derivative of that, okay, if I take the derivative, that's going to be 3x squared plus 4x minus 5. Okay, that's a parabola. That's this parabola, this green parabola right here. Okay, that's the slope of the purple curve. And then if I take the second derivative, that's going to be 6x plus 4. That's just a line. Guess what? That's that blue line right there. Okay, so if you kind of look at this stuff, it kind of tells you what's going on. Remember, here's my original equation. And the green tells me the slope. So the slope is positive up here, but it's getting smaller, okay, until it reaches a slope that's 0 right here. Oh, look at that. The slope is 0 right there. Okay. Then the slope turns negative. Okay. And sure enough, the slope turns negative. Okay. Until it reaches 0. Yeah. It takes negative. The slope reaches 0 right here. There's the slope of 0. Now it's positive again. There. Now the slope is positive. It's going back up. Okay, this tells you the concavity. The concavity is down all the way to here. So you can look at the curve. The concavity is down to here. Then it switches over. Now the concavity is up because it's positive right here. There's where it switches, right there. Okay. So I think it's a helpful little graph to have. You know, the slope is positive, but it's decreasing. The slope is increasing and it's positive. All right, you can take a look at that picture and kind of analyze that a little bit, and it'll tell you quite a bit. Okay, determine the open intervals upon which the graph of x squared plus 1 over x squared minus 4 is concave up or concave down. All right, so we got some derivatives to do here. So f prime of x, quotient rule, x squared minus 4 times 2x minus x squared plus 1 times 2x all over x squared minus 4 squared. All right, let's simplify this a bit. This is going to be 2x cubed minus 8x minus 2x cubed plus 2x. Remember, that's all in parentheses because it's minus all that stuff over x squared minus 4 squared. I think it's easiest to just leave it like that. So f prime of x. Here, let's do this. We'll make that positive, negative, and negative. So then this becomes 2x cubed minus 2x cubed. That goes away. I get negative 8x minus 2x, negative 10x over x squared minus 4 squared. Okay, so there's my first derivative. Now I got to take a second derivative. So f double prime of x is going to be x squared minus 4 squared times negative 10 minus negative 10x times 2 times x squared minus 4 to the first power, chain rule, 2x all over x squared minus 4 squared squared, so that's going to be the fourth power. Now let's simplify this thing. Let's see. What can I do here? Oh, you know what? Let's do this. I've got an x squared minus 4. I've got an x squared minus 4 and x squared minus 4. So let's cancel. I can cancel 1 out of there, 1 out of there, and 1 out of here. And then I can distribute the negative 10. So I'm going to get negative 10x squared plus 40. These will cancel. And I'll get 2 times 2 times 10 is going to be 40 x squared all over x squared minus 4 to the third power. And those will combine like terms. And I get 30 x squared plus 40 all over x squared minus 4 cubed. I don't know, they factor a 10 out. They do, they factor out a 10. So I get 3x squared plus 4 over x squared minus 4 to the third power. There's my second derivative. Okay, so when's this thing going to equal 0? Well, when the numerator equals 0, and that would be when 3x squared plus 4 is 0. So 3x squared would equal negative 4, x squared would equal negative 4/3, and that's never going to happen. So I'm not going to have anything there to worry about. I'm going to have an issue on the bottom when x is plus or minus 2, because that means that the denominator will be 0. So x plus or minus 2, that's my critical points I got to deal with. All right, so I'm going to region test this thing at plus or minus 2. Let's see here. All right, so if I do that, f double prime of negative 3, f double prime of 0, f double prime of positive 3. So let's see, if I plug in 0 into this, that's usually easy to do. That's going to give me 4 times 10 is going to be 40 on the top. And it's going to give me negative 4 to the third power. That's going to be negative 64. So that's negative, which means it's going to be concave down. Now, don't just assume it's going to go up, or down, up, down, or whatever, because that sometimes that doesn't happen. All right, so let's put in 3, because that's another easy one to do. 3 is going to give me 27 plus 4 would be 31 times 10 would be 310. Doesn't really matter, it's just positive. In the bottom, I'm going to get 9 minus 4 is 5, cubed is 125. Again, it's positive, this is concave up. And over here, if I put in negative 3, well, this is still going to be positive on the top, because when I square it, it's going to be positive. Again, I square it, it's going to be positive. So it's going to be the same answer as this one. It's going to be concave up as well. Okay. Points of inflection. Let f be a function that is continuous on an open interval, and let c be a point in the interval. if the graph of f has a tangent line at this point C, f of C, then this point is a point of inflection of the graph. This point is a point of inflection of the graph of f when the concavity of f changes from upward to downward or from downward to upward. Okay, so essentially, that's also true if f double prime is 0. If f double prime is 0, that's an inflection point. The definition of a point of inflection requires that the tangent line exists at the point of inflection. Some textbooks do not require this, but ours does. So here we've got one. It's a piecewise function. It's x cubed when x is less than 0, and it's x squared plus 2x when x is greater than or equal to 0. That does not have an inflection point at 0 since it's not differentiable. You got this sharp corner right here, and you got multiple things that could be tangents there. So yeah, that's not going to be differentiable. Okay, so here you go. Take a look at these problems, and if you have any questions, you can hit me up in class.